The history of quantum computing can be traced back to the early 1980s, when the first quantum algorithm was discovered by mathematician Paul Benioff. In 1985, David Deutsch, a physicist at the University of Oxford, proposed the concept of a quantum Turing machine, which laid the foundation for quantum computing. In 1994, Peter Shor, a mathematician at Bell Labs, discovered the first quantum algorithm that could solve a problem exponentially faster than any known classical algorithm. This algorithm, called Shor's algorithm, is able to factorize large integers in a fraction of the time it would take a classical computer. Since then, research in quantum computing has continued to advance, with scientists and engineers working to develop practical applications for this technology. Today, quantum computing is being researched and developed by many companies and organizations, including Google, IBM, and Microsoft, as well as government-funded research institutions such as NIST. Quantum computing is a type of computing where information is processed using quantum bits instead of classical bits. These quantum bits, or qubits, can exist in multiple states simultaneously, known as superposition, and can become entangled with other qubits, which allows for powerful parallel processing. This allows quantum computers to perform certain types of calculations much faster than classical computers. However, they are still in the early stages of development and are not yet widely available. In classical computing, information is processed using bits, which are binary digits that can have either a value of 0 or 1. In quantum computing, information is processed using quantum bits, or qubits, which can exist in multiple states simultaneously. This is known as superposition. For example, a qubit can exist in a state of 0 and 1 at the same time, whereas a classical bit can only exist in one state at a time. This allows quantum computers to perform certain types of calculations much faster than classical computers, because a qubit can represent multiple values at once, enabling a quantum computer to perform many calculations simultaneously. Another important aspect of quantum computing is the concept of entanglement. This refers to a phenomenon where two qubits can become connected in such a way that the state of one qubit affects the state of the other, even when the qubits are separated by large distances. This allows for even more powerful parallel processing in quantum computers. It is important to note that the qubits can exist in multiple states simultaneously only when they are not observed or measured. Once the measurement is made, it collapses into one state. The ability to observe the qubits in multiple states is the key feature that enables many quantum algorithms. Quantum computing is still in the early stages of development and is not yet widely available for commercial use. However, it has the potential to be particularly useful for certain types of problems that are difficult or impossible for classical computers to solve efficiently. Some of the potential applications of quantum computing include drug discovery. Quantum computers can simulate the behavior of molecules and chemical reactions, which can be useful for discovering new drugs and materials. Machine learning. Quantum computers can perform certain types of machine learning tasks, such as image recognition and natural language processing, more efficiently than classical computers. Optimization. Quantum computers can solve complex optimization problems, such as scheduling and logistics, more efficiently than classical computers. Financial modeling. Quantum computers can model complex financial systems more efficiently than classical computers, which can be useful for risk analysis and portfolio optimization. Climate modeling. Quantum computers can simulate the climate and the Earth's systems in more detail than classical computers, which could provide a better understanding of climate change. It is worth noting that these applications are still in the research and development phase, and it's uncertain when, if they will be, fully developed and implemented. If you enjoyed this video, please consider leaving a like, commenting below, and subscribing to the channel for more videos like this.